The wings support the weight of the aircraft in the air, and so must have sufficient strength and stiffness to be able to do this. Their strength and stiffness is determined by the thickness of the wing, with the thickness and type of construction used being dependent on the speed and weight requirements of the aircraft. The types of construction are biplane, braced monoplane, and cantilever monoplane. Very few biplanes fly at more than 200 knots in level flight, so the air loads are low, which means that a truss-type design, which is covered in fabric, is satisfactory. The wing spars, interplane struts, and bracing wires form a lattice girder of great rigidity, which is highly resistant to bending and twisting. Unfortunately, this system also generates a relatively large amount of drag, which accounts for the fact that biplanes fly relatively slowly. In flight, the flying wires hold the wingtips down and support the fuselage. On the ground, tension in the landing wires supports the wings. In the braced monoplane type of design, the wing is connected by a brace to the fuselage or landing gear. In flight, the brace is subject to tensile loads and acts as a tie. On the ground, it is under compression and acts as a strut. To provide fail-safe protection, the brace is often made from more than one member. The Shorts Skyvan, for instance, has 3 members per brace. This type of design is mainly used on low-speed aircraft. Now we will look at cantilever wings, the design used by most modern airliners. The wings have to absorb the stresses due to the lift and drag in flight, and, if of this design, their weight when on the ground. This is achieved by building the wing around one or more main load-bearing members known as spars. The wing spars pass from wingtip to wingtip either as single structures or as connected sections. The spar will normally be an I-beam either manufactured as a single part or made up of 2 or more parts to give it fail-safe characteristics. These are constructed so that they will absorb the downward bending stresses when on the ground and the upwards, rearwards and twisting stresses when in flight. In flight, bending stress relief is provided by mounting engines on the wing and by locating the major fuel tanks in the wing. Fuel usage procedures are designed so that the wing tank fuel is used last. This is of particular importance at high all-up weights when the outer wing fuel tanks should be full. As fuel is used, the weight of the aircraft decreases, which reduces lift required and therefore the wing bending moment. The wing may be of a single spar, twin or multi-spar construction. A conventional structure would consist of front and rear spars, stringers, and ribs, with the metal skin attached to them to form a torsion box. The torsion box functions as a beam, but is considerably lighter than a solid beam of the same size, without losing much strength. The stressed skin takes the loads due to the differences in air pressure and the mass and inertia of the fuel in the wing tanks. It generates direct stresses in a span-wise direction as a response to bending moments, and it also reacts against twisting forces. Stringers are span-wise members which give the wing rigidity by stiffening the skin in compression. In most modern aircraft, they are formed by machining integral ridges into the skin. Ribs maintain the aerofoil shape of the wing, support the spars, stringers, and skin against buckling, and pass concentrated loads from the engines, landing gear, and control surfaces into the skin and spars. Ribs often have lightening holes cut into them. As well as reducing the weight of the structure, these holes are usually flanged to help stiffen the rib. The major structural components of the wing are generally manufactured from aluminium alloys. With composite material, such as glass-reinforced plastic or carbon-reinforced plastic and honeycomb structures being used for more lightly loaded structures. Carbon-reinforced plastics are gaining wider acceptance for the manufacture of major structural components, such as the fin and horizontal stabilizer. There are a number of aircraft mass limitations that you must become familiar with. The maximum zero fuel mass of an airplane is defined as the maximum permissible mass of an airplane with no usable fuel. This limit is set by the maximum bending load that the wing root is able to support. The maximum zero fuel mass sets the maximum load that can be carried in the fuselage. Fuel added to the wing will not increase the wing bending load. In fact, it will reduce it. Maximum structural takeoff mass is the maximum permissible total airplane mass at the start of the takeoff run. Maximum structural taxi mass is the maximum mass of the airplane at the commencement of taxi. This is sometimes also referred to as the maximum ramp mass. Maximum structural landing mass is the maximum permissible total airplane mass on landing in normal circumstances. Flutter of the wings can be prevented by using the engines as mass balance. This is done by mounting them on pylons forward of the wing leading edge. The fact that an aircraft is poorly maintained, particularly in respect to excessive control surface backlash or flexibility, may mean that flutter will occur at speeds below the limit airspeed. This is the end of the lesson. You should now understand the differences between truss, monocoque, and semi-monocoque fuselage construction, and the differences between biplane, braced monoplane, and cantilever monoplane wing constructions. You should also note the following key points from this lesson. Spars on non-stressed skin wings absorb the downward bending stresses when on the ground, and the upwards, rearwards, and twisting stresses when in flight. On stressed skin wings, they are assisted in this by the skin itself. On larger aircraft, a wing torsion box is often formed from spars, skin, stringers, and ribs. Fuselage stringers stiffen the skin and assist the sheet materials to carry loads along their length. On pressurized aircraft, they take some of the strain caused by the pressurization and convert it into tensile stress. Flutter can be prevented by mass balancing control surfaces. Finally, you should know the meaning of the various maximum structural masses to which an aeroplane is limited. Remember that the maximum zero fuel mass of an aircraft limits the bending moment at the wing root, while allowing the maximum load to be carried.